circle around the magnetic field lines. And now we looked at the case when we had an electric field also in addition to the magnetic field. And we saw that, for example, if you exert a electric field in the z direction, the electric field in the z direction, magnetic field in the x direction. In that case, the object carries, the trajectory of the object is what is called a cycloid. So it doesn't really move in the z direction, in the direction of the electric field, but it moves perpendicular to it due to the presence of the magnetic field. And hence, in this sense also, although the magnetic field doesn't do any work, it just rotates the direction of the effects of the electric field, let's say. So the electric field will be pushing the charge in the upward direction, whereas due to the magnetic field, it gains almost, on the average, a constant velocity in the perpendicular direction. So this was what we had done until now on magnetic fields. Now, do you have any questions on magnetic forces or anything else? Now, this week we will start studying what is actually creating this magnetic field. Now, last week we looked at the problems where there was already a magnetic field, and this magnetic field exerted forces. This week we will start by asking the question, what creates this magnetic field? So before we start, no questions?
Can you please explain a little bit about the second question of the homework? I didn't understand what the question is asking. The sphere is an electric field.
The sphere is in a dielectric, right? No.
The sphere that is in an electric field or magnetic, no, it was an electric field, and with the epsilon, and you said that if the sphere is inside inside the electric field by epsilon 2, find the electric field inside the sphere.
Everywhere. So basically you have this case. We already looked at the problem of a dielectric in a uniform electric field. Now in this problem I tell you that this dielectric is inside another dielectric. It's not vacuum outside. Now what changes? This is the question. So the strategy is basically the same, with some modification due to the fact that outside is not a vacuum. Okay, so we will see that the magnetic field is mainly created by currents. And so let's first discuss what we mean by currents. Now, most of the time we are familiar with the currents that are running along wires. So if you assume a very thin wire, there is a current running I through it. So if somebody tells you that there is a current I running through this wire, what that means is you just take a point, at this point A, let's say, you count the number of charges passing through that point in a given time dt. This is what we call the current. Now, for us, it will be important to also pay attention to the direction of the current. In the wire, the current will always lie along the wire, but it can run in this sense or in the opposite sense. So for us, that will be important. Well, your book prefers to call it a vector, the current as a vector. I don't like that notation. The current is just a number, a real number. I don't think it shouldn't be classified as a vector. We will see why it's not really a vector, although it has a sign. The sign is will be important. It's not a vector. Now, most of the time we don't have this, let's say, very thin wires. The wire has a cross section. So we would have regions of space where the charges will be moving. I say this can be a wire, this can be, in fact, any region of space. It doesn't have to run along a wire. You just can take, for example, consider the solar winds. So when we talk about solar winds, we are basically talking about charged objects like the electrons and the protons that come in our direction from the sun. But if you have these charged objects that are moving, that makes a current. There's a current due to in this solar wind. And of course, in this, if you just assume this region in which there are charges moving, you can just assume that you divide it into very small filaments. This is very thin. So certain charged objects will start from here, flow along this trajectory in this region. There is no such conductor. This is not necessarily a conductor, by the way. So there are charged particles which are basically moving along this region. I just follow the trajectory of, let's say, some of them. They will start from here, and they will just move along this line. So I will just imagine this hypothetical surface which confines this current. Now I can talk about the total current running through this very thin filament. So that dI. We can define it. It is just defined just like that. Just take a point on this very thin tube. Consider a point, count the charges passing through a unit time. Now this current will be very small, and in general the current will be proportional to the area of cross-sectional area of this filament. So we will just divide it by the cross-sectional area, dA. Now this is what we call the current density. Now this will be a vector, the current or not K, but J. The direction of J is along this line. So you can, if you just follow, at this point, the current carrying objects will move with some velocity v in that direction. And we will see that J is parallel to v. Now let's also look at how the velocity is related with the current and hence the current density. Now let's go back to this example of a single wire, a very thin wire. We are waiting a time dt and counting all the charges that passes through the point A. So that is how we can obtain the current. Now the charges in this wire will be moving with some velocity v along this wire. In a time dt, they will just cover a distance. Let's say this is dl, where dl is nothing but their speed multiplied by dt. So after a time dt, the last charge within this segment passes through this point A. So within that time dt, all the charges within this length passes through A. And the total number of charge in that length, which we call dq, dq is nothing but the charge density times dl. This is what will be the total charge in that region, in that length. And hence, this is the charge that passes through this point A in a time dt. Do you agree? I don't know. When there's a problem, you are also silent. When there's no problem, you are also silent. So dq is nothing but lambda v times dt, and hence dq by dt is lambda times v. Well, we can just repeat the analysis for in this problem. Just take a very small length here. That length, dl, is nothing but v dt. We just need to count the total charges passing through this area in a time dt. So those are the charges within this volume. The height of this volume is V times dt. The cross-section is, we say, dA. So the total number of charges within that volume is nothing but the volume density times the volume of that segment. Well, the volume is nothing but dA times the length, dAv dt. So dq by dt is nothing but the current passing through that point. If we divide it also by the area, this is the current density. So, and this is equal to rho times V. And hence the current density will be rho in the V direction. So this is a vector. And if you want to calculate the total current running through a given area, you see this current density is the current per unit area. So you just multiply J by your area, vector this time, the area vector, and integrate it over your area vector. This gives you the total current running through your area. Well, you see, there is a scalar product over here, so I is a scalar, not a vector. And of course, this J can be running in the direction of A or in the opposite direction. So if J is in the same direction as your area vector, then you have a positive current. If J is in the opposite direction, then you have a negative current. But nevertheless, the current is always a number. Because you see the definition of J, just think of like this. You have all these charged particles moving in one direction. Okay, so you can take an area. You can calculate the current passing through that area. And then you can define the current per unit area. This is what we call the J. This is the current per unit area. So if you multiply it with the area, you get the current passing through that area. Well, what is the dq is the total charge in that volume, right? So the charge density is nothing but the charge per unit volume. So total charge in that volume will be nothing but rho times the volume. Now, this is the total volume. We have it's just like a rectangular prism with a base area dA and the height v dt. So this product is the volume of that segment. Charge density times the volume just gives me the total charge within that very small volume. So J, I repeat, is again the number of charges passing through a unit area per unit time. So this is what our J. Now let's consider a closed area. So we have this area. I have my dA vectors, always perpendicular to the surface. I can have some current density in that region. Then J dot dA, you see, J is the total number of charges passing through an area per unit time. J dot dA is the number of charges passing through this dA per unit time. So I just imagine a small area over here, let's say. J dot dA, J at that point, multiply with the dA vector at that point, gives me the total number of charges passing through that area per unit time. Well, if I just integrate it or sum over all of this area, what I obtain is the total number of charges passing through all of this area in the direction of dA. But then let's say if in a given amount of time, the total charge passing through this area is, let's say, 5 coulomb, then the charges inside has decreased in the same amount of time by 5 coulombs. If the charges are passing through the surface, then the total charge inside is decreasing, right? So let's say if the number of students going out of this classroom is 5, then the total number of students in the classroom has decreased by 5. So let's say Q is the total charge inside my volume. So the amount of charge, the change in the charge per unit time is nothing but dq by dt. Well, if this is positive, that is, if there is the number of charges passing through the surface area per unit time is positive, that means the total charge inside per unit, the change in the total charge inside per unit time is negative. So we have this minus sign, so we should have this relation. So if the total charge within a given volume is decreasing, that basically tells me that there is a current on the surface of that volume. Now let me rewrite this total charge in a different form. This is equal to minus d by dt rho dv. In this volume V, and here this integral is over the surface or over the boundary of the volume V. Let me just rewrite it in a slightly different form, explicitly stating the arguments. J at the point R at the time t, dA, integrated over the boundary. This should be equal to minus d by dt rho at the point R at the time t, or minus del rho by del t evaluated at the point R at time t. Well, you see here I have a total derivative over time because rho depends on both the position and the time, but I'm integrating over all the positions. So this integral depends only on time. It doesn't depend on positions. But when I move this derivative inside, I am only taking the derivative with respect to this one, so that then it becomes a partial derivative. Now let me do another trick on the left-hand side. This is an area integral, but I can convert it into a volume integral. The left-hand side is nothing but the integral of the divergence of J at the time RT, integrated over the same volume. Or del rho by del t plus the divergence of J integrated over this volume V. This is always equal to 0. But keep in mind that we started with an arbitrary volume. Instead of this volume, I can just do all the same arguments for a smaller volume. For a volume that looks like this, whatever volume you choose, our arguments that we use over here will still be valid. And hence, the integral of this quantity is always 0, whatever the volume you choose. But that is only possible if del rho by del t plus the divergence of the current density is equal to 0. This is what we call the continuity equation. It is just an expression, it just expresses the conservation of charge. So if the charge density in a given region is changing, it is basically because there is a current over there. So without a current, the charge density cannot change. Now we will be dealing with magnetostatics. We are dealing with a system that is static, that is not changing in time. So in magnetostatics, d rho by dt, this is equal to 0. And nothing can change in time in a static problem. So this basically tells me that we have the currents that we will be studying will always have their divergences equal to 0.
Eğer bu sıfır olmasaydı akım hep değişecekti.
Yes. If divergence of the current is non-zero, then the current density at certain regions should be changing in time. Either you have accumulation of charges somewhere, or there's a depletion of charges somewhere.
What is the derivative of charge density with respect to T0?
Well, that is the definition. That is what we mean by static. Static means nothing changes in time. So we are not looking at an arbitrary phenomena involving currents. We will, for the time being at least, we will only be dealing with phenomena that are static, that do not change in time.
Yani o zaman yüklerin sabit hızla gittiği.
Well, not necessarily. You see, if you have such a wire, well, the velocity of the charges are not the same in this one. The velocity constantly changes.
O zaman manyetik alan değişimi olmaz mı?
Well, you see, as long as there are no accumulation of charges, no. Just think of it like this. You have a water pipe. There's a water flow. And the cross-section of your pipe changes. And you are pushing it such that the speed of the water is constant over here, and it will be constant over here, but they will be different. So the speed of water changes as they move along this pipe. Nevertheless, the system is static in the sense that if you look at this point, the velocity of the water at this point is always the same. If you take a single water molecule and follow it, here it will move slower, here it will move faster for a single water molecule. But when you look at the system, the velocity of the water molecule at this point is always the same. The velocity of the water molecule at this point is always the same. The same thing applies for charges. If you just follow a single charge, its velocity can change as it moves along the current. But the system as a whole, looked at it as a whole, if you just look at the current passing through a given point or the current density at a given point, it is always constant.
Hocam şimdi dedik ya, hani bu continuity equation, işte yüzeyden geçiyor, continuous devam ediyor yani. Şimdi akımın yönünde elektrik alan oluşuyor. Akımla aynı.
Okay.
Aynı yönde işte. Hani elektrik alanında da discontinuity demiştik ya yüzeyden.
Hı hı.
Bununla arasında bir çakışma var.
Why?
Ya burada continuous diyoruz ama
What is continuous?
akım.
Not necessarily. I mean, just imagine a wire. Inside there is a current, outside there is no current. The current is not continuous. The continuity over here is not saying that the current is continuous. It just states that the charges, the existence of charges, let's say, is continuous. In the sense that, for example, you can have charge conservation if you just make one charge disappear over here and appear in, I don't know, in Andromeda galaxy at the same time. That is continuous. That is conserved, sorry. But that is not a continuous conservation in the sense that it just disappeared over here and appeared somewhere else. If the charge at this point changes, it is because they have moved at the next point in some direction. In that sense, it's a continuity equation. It doesn't say that the current is continuous. the flow lines of the current will be continuous. So if you just follow the trajectory of a line, of a charge, it will just flow continuously. It will not stop here and start over here. That is the continuity we are referring to over here. Well, using these laws, you can just go back to the force acting on a current carrying wire, for example. You see, what we know that the force acting on a point charge was this one. So if you just consider the charges in a current, F would be just integral of V cross B times dq. So you have all these charges moving with a velocity v, let's say. You divide all these system of charges into small bits, small point charges, each one having a charge dq. You just calculate the force acting on each one of these charge dq and sum them up. And that gives you the total force acting on your system. But for a linear charge density, dq is nothing but lambda times dl. But now we have lambda times v is nothing but the current. And dl vector is parallel to v. So I can just convert this into I times dl cross b. This is the force acting on a wire. If you have a volume charge density, then force will be v cross b times rho dv, rho being the charge density, and hence this just becomes J cross B dV. This is the total force acting on a volume charge density as it is moving in the presence of a magnetic field. Now let us look at any questions up to this point on the currents, how we define them, what they mean, the continuity equation, the conservation of charge. Which one? This one. Well, you see, this is the force acting on a system of charges. We just divide it into very small parts, dq. Each one would feel a force dq v cross p. Okay. Then for a volume charge density, dq is nothing but dq would have some volume dv, and we have the charge density. For a volume charge density, dq is nothing but rho times dv. dq will correspond to a volume dv, and at that point, let rho be the volume charge density. So rho times dv is nothing but the volume of the charge of that volume dv. So I just replace that dq by rho times dv. This is dq. Okay, just keep in mind, I have a small v here. This one is the capital V. Small v is the speed or the velocity. The capital V is the volume.
Hocam şimdi şurada hani diğer cross B oldu ya.
Evet, yes.
O integralden nasıl?
Well, let's do an example. B is uniform. The simplest example. Well, df is nothing but I times dl cross B. Well, B is uniform. It's a constant. I can take it out of the integration. I is constant. I can take it out of the integration. So this is equal to I times dl cross B. Or the df is equal to I times the final point of my wire minus the initial point of my wire cross B. Now, the uniform B case is the easiest one. Now, the unit of current. Sorry?
Is it DF or F?
F. It's the total force. Now let's also go over the currents. The units. Well, the unit of current is the coulomb per second, which we define as the ampere. The current density is, remember, the current divided by area, which is the ampere per meter squared. Now, finally, let's see how we can calculate the magnetic induction. So we have this steady current, this current that doesn't change in time. There is a wire carrying our steady current. We will assume some length, dl, some segment of this wire. I will denote that segment by this vector dl. dl vector, the length of this dl vector is equal to the length of my segment, and its direction is along the direction of the current. Then I can talk about the contribution to the magnetic B field at this point. Let us say this is the point R. This is the point R prime. Then the contribution of this segment to the total B field at the point R would be given by, it will be proportional to dl cross R minus R prime divided by R minus R prime cube. So what is the direction of this vector? You see, this vector over here is the vector R minus R prime. So dl cross R minus R prime is out of dl cross R minus R prime is out of the screen. So the dB vector will be out of the screen. The contribution to the magnetic field at this point due to this very small segment is out of the screen. Well, that is a proportionality, and the proportionality constant is conventionally written as mu0 over 4 pi. Where mu0 is just some constant, mu0, it is defined to be 4 pi times 10 to the power minus 7 Tesla meters. Tesla being the unit of the magnetic field. By the way, this is a definition. This is exact. It basically defines what we mean by Tesla, by 1 Tesla. And conventionally, this is chosen to be, that coefficient is chosen to be 4 pi times 10 to the power minus 7. So if you want to calculate the total magnetic B field, total B field, it will be just the integral. So there's an I over here. I dl cross r minus r prime divided by r minus r prime cubed. Or, well, if you just look at over here, for a linear charge density, we have I times dl, which becomes, for a volume charge density, is just J times dV. You can just make that replacement. And this law you can also write as mu 0 over 4 pi J cross r minus r prime divided by r minus r prime cubed, integrate over the volume. Well, to make a direct transition, just observe that I times dl. I is nothing but J, the current density, times dA, dl. But dl is along the wire, which is along the current. The current is also along the wire. So this is equal to J dA times dl, but this is nothing but dV. So whenever you have I times dl, you can always write it as J times dV. If you have a single, very thin, a single wire, then J just becomes a Dirac delta. You just take the additional two integrals, and this is what you would obtain. Now, this basically allows us to calculate the magnetic induction for whichever current system you can imagine. And then let's do some applications. Well, let's assume we have an infinite wire carrying a current I. And we would like to find the magnetic induction B field at this point. Well, we need to carry out this integral. B would be mu 0 over 4 pi times I dl cross r minus r prime divided by r minus r prime cube. This is the B field at the point R. So let's start by dividing our line. This is my dl. Well, this is the vector r minus r prime. R minus r prime is nothing but the vector pointing from the source to the measurement point. First of all, what is the direction of dl cross r minus r prime? Let's choose our axis. Let's say this is the x, this is y, this is z. What is the direction of dl cross r minus r prime? This is dl, this is r minus r prime, dl cross r minus r prime, this is in the plus z direction. Let's say this angle over here is theta. So it's in the plus z direction. What is the magnitude? The magnitude of r minus r prime times sine theta, the angle between the two. So the magnetic field, the B field, we can write as mu 0 over 4 pi I. Well, note that whichever segment you can imagine, whether here, here, or here, dl cross r minus r prime is always in the z direction. So the magnetic induction at that point will be out of the screen in the plus z direction. In the z direction, the integral of dl over r minus r prime times sine theta. Well, let's say this is d. My point is at a distance d from my wire. Well, this basic, you see, here I'm integrating over along my wire, that is dl. As I'm moving along the wire, the angle theta will change, this r minus r prime distance will change. So all of these things actually depend on whatever you call L, or you can say that everything depends on r theta. I will choose the theta. So I will try to write everything in terms of theta.
I think these, what inside the integral is dl over magnitude
Squared. Yes, you're right. So here I have a cube. I also have another one over here. It cancels one of them, so I'm left with square. Well, I know that d is equal to r minus r prime times sine theta, or r minus r prime is equal to d over sine theta. So at least that kind of gets rid of one of the variables, or expresses one of the variables in terms of theta. So let's write them first. dl times sine theta times sine squared theta over d squared, or mu 0 I over 4 pi d squared in the z direction, dl times sine cubed of theta. Now let's look at what is dl. How can I express dl in terms of my other parameters? Now let us see. Let me call this length L. So basically, each segment, I can specify their position by telling you the L value. And L differs by dl between each of these segments. So that's why this is L, this is dl. But you see, L is equal to, or d over L is equal to tangent theta. Or L over d is equal to cotangent theta. dl over d, I am taking the differential of both sides. This will be equal to, what is the derivative of cotangent theta? That is the derivative of tangent. Minus 1 over sine squared theta, d theta. So this is equal to mu 0 I over 4 pi d squared in the z direction. Instead of dl, I have d times minus 1 times 1 over sine squared theta d theta times sine cube theta. Well, this d cancels this d over here. This sine squared cancels two of these sines over there. So we have minus mu 0 I over 4 pi d in the z direction of sine theta d theta. Now, what are the limits of theta? You see, this is how I define theta. So what is the initial value of theta? Well, you see, what is the smallest value of L? Now, what is the smallest value of L as I'm moving along this wire? It's minus infinity. You see, I start from well, that is one place where I wasn't so careful about. So what is dl, what is the direction of dl, etc.? dl is in this direction. So this dl appearing over here is something, it has to be something positive. That is how I defined it along this direction. Okay? But as I move from this point to this point, the change in L is negative. dl, in that sense, is not really equal to the change in L. dl is equal to my negative of the change in this L as I'm moving along the direction of the current. Or I can say that I'm moving in the opposite direction. That means I start from here, then theta is pi. So theta starts from pi and eventually it goes to 0. This is minus mu 0 I over 4 pi d times minus cosine theta as theta goes from 0 to pi. Now pi to 0. Minus minus, it makes a plus cosine 0. 1 cosine pi. So this is mu 0 I over 4 pi d in the z direction. 1 minus minus 1. This is equal to mu 0 I over 2 pi d in the z direction. You see, the critical thing is you have to be careful about your definitions. This L, it starts from minus infinity. Since it starts from minus infinity, well, if it starts from minus infinity, theta starts from pi. Did I make any other mistakes? Which one?
Yukarı dediniz ya, şurada elin sınırlarını belirlerken.
Well, okay, so I would have probably chosen, since I already chose my x-axis over there, I would have chosen a dx over here in this direction. So that would have made my life a lot easier, but I should have paid attention to this angle here. I would have defined as theta, just like that. This angle is pi minus theta. So I would repeat everything with pi minus theta angle over here. It would have made my life and your understanding easier. But then I would have to justify why did I choose that large angle as my variable. You see, if you look at this one, this expression over here, in all our definitions, we said that dl is positive. You see, here we put the magnitude of dl. dl has to be positive. That means the theta is negative. So we should be reducing theta, starting from our initial point. So the largest value of theta, is when this point is over here at infinity. And theta, as we go along, it becomes larger and larger. It reaches 90 degrees. It becomes larger and larger. Eventually, it reaches 180 degrees or pi radians. So we should start from there and go back to make sure that this dl that we used over here is positive. Because of this relation between dl and d theta. This kind of dictates this relation, and our convention that dl should be positive dictates which extremum we start from and go to the which one. So this relation told me that I start from theta is equal to pi, not theta equal to 0.
So why is integral from 0 to pi?
It's pi to 0. My integral is from pi to 0. From pi to 0.
Pi is the maximum, right?
Yeah, pi is the maximum. That is the beginning. But the theta starts from taking the value pi. And then theta gets smaller and smaller. And at the end of my summation, theta takes the value 0. That is why the lower limit is pi. Theta starts from its largest value. Well, you see, you get the correct answer eventually. But what if the problem is a bit more complicated? What do you do then? Just add some signs here and there until you get the correct answer. So what is the correct answer if nobody has solved it before? Okay, let's give a 10-minute break and then we will continue.